Let's talk about real zeros of polynomial functions. So what is a polynomial function? A polynomial function of degree n, where n is the highest power, it has the following form. And what do polynomial functions look like? Polynomial functions are smooth and continuous. So this one is a function, is a polynomial function. That one is not a polynomial function because it has a gap right there. This one is also not a polynomial function because it has a vertical and a horizontal asymptote. And the last one is a polynomial function, smooth and continuous everywhere. Now that we have the form of a polynomial function, we can discuss its end behavior. Now with end behavior, we have no clue what happens in the middle of the function, but we do know what happens as x values approach negative infinity and positive infinity, very large and very small values. And everything depends on the leading term. So what we see here is if n, or the degree, is odd, we have the following cases. If n is even, we have these cases that ends both up or both down. And which case it is depends on whether the leading coefficient is a positive value or a negative value. And let's quickly talk about extrema. Extrema is just a term to collect of both relative maximum and relative minimum values into one term. And what do the extrema look like? Here is a relative maximum. Every point around there is smaller than it. Here is a relative minimum. Every point surrounding it is larger than it. Here's another maximum. And this point is actually neither a relative min or a max because it has points that are smaller than it and larger than it and within its relative area. So this function would have 1, 2, 3 relative extrema. The maximum number of extrema for any polynomial is one less than the degree, or its highest power. So, for example, a function whose degree n is 12 can have a maximum of 11 extrema. So end behavior tells us what happens at the extremes, or the outside of the function. And what happens in between, we often look at the zeros. They're often the most important values. So it's pretty clear here that the zeros are -3, -1, and +2. Now, multiplicity tells us what the shape looks like as we arrive there. If you kind of zoom in at -3 and look, it goes straight through. It appears like it's a linear function. So that tells me that the multiplicity of that function, of that zero, is simply 1. If I look at x equals -1, it looks kind of like a quadratic, and it looks like the parabolic. It kind of bounces off the axis there. So that's going to be a multiplicity of 2. In general, really all we know is it's an even. It could be 2, 4, 6, 8, but for our purposes, we're going to assume that it's 2. Finally, at x equals +2, it kind of flattens out like a cubic function. Comes down and kind of flattens out there, and that's actually going to be a multiplicity of 3. And what this means is what the factors would look like are x plus 3 to the first power, x plus 1 squared, and x minus 2 to the third power. So here's a quick example of long division of polynomials. Here we're dividing 6x cubed minus 19x squared plus 16x minus 4 by x minus 2. As you can see, all the steps work it out here. First, you multiply 6x squared times x and get 6x cubed, 6x squared times -2, and we get -12x squared. We then subtract these, which is why you see we end up with -7x squared, bring down the plus 16x, and then simply repeat the process. The big idea with this is then we can take this and factor that function into x minus 2 since there was no remainder. We know that x minus 2 is a factor in 6x squared minus 7x plus 2. our quotient. I can further factor 6x squared minus 7x plus 2 into 2x plus 1 times 3x plus 2, and that function is completely factored. Synthetic division of a polynomial is a shortcut for long division, and it only works if I'm dividing by a factor of x minus k. It has to be in that form, of 1x minus k. And this is the pattern we use. First, the most important thing is, if it's x minus k, I take positive k here. Bring the a down, multiply a times k, add, repeat. So how does all this come together? Suppose I had a function f of x equals 2x to the fourth plus 7x cubed minus 4x squared minus 27x minus 18. And I was also given that the quantity x minus 2 and x plus 3 are factors of it. And I want to factor it completely. First, I'd say, let's take, since we know the factor is x minus 2, use synthetic division. Since we have a remainder of 0, we know it is truly a factor. Repeat, bring all those coefficients down, and divide it by x plus 3. That gives me factors of 2x squared plus 5x plus 3. That factors further into 2x plus 3 and x plus 1, meaning the complete factorization of that function is seen here. So putting this all together, we can sketch a reasonable graph of the function. Looking at the leading term, 2x to the fourth, the 4, or degree n of 4, it tells us that the function is either ends either all up or all down. And the fact that 2 is a positive number tells us that the end behavior is positive infinity and positive infinity. Now let's look at these zeros. From the factored form, we have that the zeros are 2, negative 3, negative 3 halves, and negative 1. Each one has an exponent that is not shown because it's all 1, therefore the multiplicity of each is 1. So it's going to look like a linear function when I cross through the axes. So to sketch this graph, I'm going to start with the end behavior. So I know it's got to start at positive infinity and end at positive infinity. Now in between, I look at my zeros. I'm going to place them, all of them, on the graph. There's 2, negative 3, negative 3 halves, and negative 1. I know that crosses straight through each one of them. And I'm basing the direction off the fact that I know this must connect. I don't really know how high these points go or low in between. I can find out by plugging some numbers into the function, but to get a rough sketch, again, I have that there.